introduced, and Pohle here. I won't read this whole thing, don't worry. This is just approved for public release, just legal. Today I'm going to be going over a new type of tool, a method, in order to evaluate a gigahertz transverse electromagnetic cell, and in order to look at basically what's the frequency limitation before you have overmoding. At that point, you can't trust your measurements if you're trying to, say, calibrate sensors or looking at different types of devices or, say, biological media. There's all sorts of uses with these chambers. And this is using basically both electromagnetic field sensors and IEC standards. And then just going over the normal, like the methodology behind it, how we're validating this and such, and then questions. Before I go into what a gigahertz transverse electromagnetic cell is, or GTEM cell, I first need to just bring up in general, just in case anyone is not aware of them, RF chambers. And so on the right here, you see what's called a anechoic chamber. And this is full of anechoic foam in the front that you see here that absorbs gigahertz types of electromagnetic radiation in megahertz. And then for anything that's in the lower frequency range, usually behind, you don't see this here, it's ferrite tiles to absorb everything. The whole point is you can get a very accurate RF measurement because you're not having, let's say, if you have a antenna, it's not scattering all over, and then you're actually measuring the scattering on top of what you're trying to radiate. So very clean, but very expensive, takes up a lot of space. And the useful part, though, is they're great for free field sensors. And then on the other end of the spectrum, so you have transverse electromagnetic or TEM cell. You can use them well for ground-based type of sensors. And the only issue, though, is when you're trying to get up to gigahertz regions, they're not good for that. They can't support it. So that's a disadvantage. But there is a an in-between here with a gigahertz transverse electromagnetic cell. And it's more of a medium footprint. They can still go as small as going onto a table, or they can get fairly large like you see here, but still can fit into a room. And they can support both free field and ground reference sensors. And they are TEM mode when you're using them. And these can support gigahertz frequencies, but there's some caveats. They can go in the low, say 1 to around 10 gigahertz. They do claim to 20, but you need to calibrate because you need to check the claims from manufacturers. The only con here, though, is that there is no like output port like the TEM does. So you can see right here when you're comparing. So you have to have other types of sensors within the GTEM cell to characterize it. And for anyone who's not aware about it, this is how they work in essence: is you have an input, you inject your RF, and then that goes into what's called a septum. So it's like a parallel plate. That's between that and the ground. Then you can get your electric field, basically with the voltage on that septum and the distance. And ideally, that should be the electric field. And then that goes into a resistor board, and then you have anechoic foam on the end to attenuate and both the low frequency, the high frequency aspects. Okay. And because we don't have a easy to use output port, we use both D dots, so they're electric field type of sensors, and B dot probes, also magnetic field sensors, in order to then measure the wave impedance, and then that's how we're looking at overmoding. And then we also then look at the IEC standards. And just for anyone who's not aware of these, so D dot probes, it's in the name, so they're displacement dipole type of probes, and it's based off the displacement equation here. So D dot equals epsilon naught, and then E dot. It's a derivative sensor, meaning you're not going to be able to measure anything that's at, say, 0 hertz. You have to have at least some type of frequency. But they're great for this, and they're also wideband. The other reason why they're used a lot in the field is because they're essentially self-calibrated based off the equivalent area of that dipole. So as long as you don't ding it and in turn doesn't pull it off, they're reliable. But they do have a limitation to some degree of where they are linear, which is around, for the smallest ones, that can get towards 10 gigahertz. And then on the other hand, we also have B-dot probes. These work essentially the same. They're also derivative, but they use a coil to then measure the magnetic flux, and then you can go ahead and get the H field off of that. So between these two sensors, you can then get the wave impedance. And something I do want to bring up, we just had our paper accepted this past week in IEEE sensors for metal 3D printing the D-dot probe. So we're able to push that towards like 12.5 gigahertz in this linear region. So if there's any interest about that questions, I can talk to you all afterwards. Okay, so methodology-wise, fairly simple for what we're doing for our experiment, but still important. We're using the VNA, doing a two-port analysis, use a directional coupler, and then we go to a power sensor that's thermal-based in order to get an accurate power reading. And then we go through a 3 dB attenuator, and the reason why is to prevent any additional reflections that could come from the GTEM cell going back into your power sensor, because we want to know what the forward power is going in. And then from there, that goes to our field probe, back to the VNA. When I was initially looking at how do I go about figuring out what's the best area to measure within a GTEM cell, I started to look at the ground plane first. So this is with the ground-based DDoS sensor. And then as a order of merit or figure of merit, looking at how closely matched the electric field is of that DDoS probe to the nominal electric field of the GTEM cell. And I'm saying nominal because to exactly know the exact electric field is not entirely true, because there are standing waves that can occur along the septum based on what's holding these up. There's basically little ropes that can be in these large GTEM cells, and that can induce perturbations. And very difficult if you're trying to do it just from the injection port. It can continue changing through. So I call a nominal. And then from there, and this is expected, at point U32, that's where we found to have the least amount of deviation. That makes sense. As you get towards the edges of the septum, you're going to have fringe field effects. That affects the uniformity of your field, won't make it as good, along with going towards anechoic foam, and as you get towards the neck. So that's what we're expecting. And then from there, if you think about like a slice in the free space, we then did a 4x4 grid with the free field DDoS sensors, and then looked at the uniformity of the electric field. This surface map right here, what you're seeing is the uniformity, so the differences between the different cells is most close towards the ground here of the GTEM cell. And as you get towards the septum, and this is still a little bit of a drop around this much towards the septum, that starts to be affected a little bit more. And that also makes sense as, again, you're getting more towards fringe field effects. So ideally, if you want like you can say least noisy and most uniform type of measurements, have it right in the middle of your device under test area and then towards the ground, and not too high towards the septum. And then from there, this is where we get into the 61,000 series of IEC standards. And so I was looking at both -4, -3, and then the next slide will be -4, -20. -4, -3 is used for usually any type of RF chamber, but you can still use it here in this case. And what it's looking at is 75% of your points that you measure. So in this case, with 16 points, 12 of them have to meet the criteria of being within 6 decibels of each other, and decibels in terms of a voltage ratio. And if they are off and there's not 12 out of 16, then it's a fail for that point. Now, if you're doing this across 10,000 data points, which I was in this case, that can become very difficult to discern. Like, you just can't really read it. And so we were thinking, okay, what's a really quick way to just quickly evaluate the performance of that GTEM cell? And that's where we came up with this binning methodology. Now, what we did was we took 10% of the total number of data points, and then we did a smoothing across. And then within that 10% of data points, we took a percentage of pass rates for the IEC standard. And then this is what we found. And again, this is just can be used as like a quick tool to see, okay, these data points in general along these regions are going to be accepted by the IEC standard. So say if you're trying to qualify parts for, say, FCC or basically telecommunications, or also looking at the, calibrating your sensors, you can rest assured most likely you're going to have a lot of frequency points that you can use there. Now, what I want to point to your attention, though, is the global minima. So this is around, at this point, this is 6.7 gigahertz. When I show the next IEC standard, this is looking very similar about the whole 75% pass rate, but instead of within the electric field within each other, this is now looking at the orthogonal fields. So more designed specifically for GTEM cells. Ideally, you want to look, the primary field should be going up and down. There shouldn't be any other orthogonal electric fields that are overrunning your measurement. And what you're doing here is you're making sure, okay, these other orthogonal fields, they're less than 6 dB from your primary. So your primary is what should be affecting your system or what you're measuring. And that global minima as well is very close to that 6.7, so in this case 6.8. And then when we compare that to the wave impedance, that's where it gets a little more interesting. And then probably not, we won't have time to do the full discussion during the session, but there's a lot of other things going on with GTEM cells, and I've seen this at multiple places. But what we're seeing here, the wave impedance greatly starts to deviate around this region for this ETS Lindgren GTEM cell that I was working with. And this red box, what we did was we measured the coax connector that was going into the GTEM cell. And then this is from their standard, where you would expect overmoding to begin. So that's up to the point that the coax can support. After that point, additional modes can start launching. Therefore, you can't trust your measurement. So this area right here, so this is around the 6.9 gigahertz region, is where it starts to greatly deviate from the expected trends here, and just any waves that can occur within these cells. But in general, this is where it started to deviate. That's where we know for sure overmoding is happening. That also starts to associate well with what we're seeing with the IEC standards. So this one requires both an E field and a H field sensor. But in this case, we could technically use the IEC standards and just use an E field sensor in order to look at where the overmoding can occur. So pretty much just using a novel bending methodology. And again, just another quick tool, could be a quick analysis for your GTEM cell. And you don't have to have both types of sensors. Say you only have an E field sensor in your laboratory. You could use this to approximate where that overmoding region occurs. Now, if you're trying to do, say, testing validations and such, you're still going to need to look at individual frequencies then and make sure they meet the standard. And as a forewarning, within that standard, right, I said 75% of the points. That means some of those points could be completely off. So if you were to measure your device at that point, it could be more than 6 decibels off as a voltage ratio. So it could be double the error, it could be triple. So you definitely want to verify, depending on the level of accuracy that you need when you're working with the GTEM cells. And any questions?